Today I will discuss a topic which should have been discussed a little earlier when we did Langevin dynamics, but which is somewhat formal and mathematical and not directly connected to the rest of the topics that we had done earlier, but it is very crucial now, becoming more and more important in the context of non-equilibrium phenomena, specific stochastic models of them, and therefore I thought I should at least mention briefly what it is all about. It has to do with our old friend Brownian motion, and if you recall, so let me start by recalling a few facts about Brownian motion. If you recall, we wrote down the Langevin equation for some Cartesian component of a particle of mass m moving in a fluid, and to quickly recapitulate what we had a formula like V dot plus gamma v is equal to 1 over m eta of t, everything like this, where this was Gaussian Markov stationary white noise, and we also discovered there was a relation between the correlation, the strength of this force and the friction constant gamma. If you put that in, we could write this, then we had a capital gamma here, so this would go to 2 gamma k Boltzmann t over m times zeta of t, where this white noise had the following properties. It had 0 mean and zeta of t prime was equal to just a delta function, delta of t minus t prime. Okay. I slurred over the fact that this quantity is not very well defined, it is too singular in some sense, in a strict mathematical sense. So we will come to terms with that now and do this a little better than what we did earlier. Now of course in the diffusion regime what happens is you are at long times t compared to gamma inverse, and then the effect of this inertia term gets negligible and this term dominates here. So let me go straight away to the diffusion regime and write the equation in the diffusion, what we call the diffusion regime, or equivalently high friction, very high friction. This equation gets replaced by x dot equal to square root of 2d times zeta of t, because recall that d was kt over m gamma. If I divide through by gamma after neglecting this, you get precisely 2d here. So all the factors are right. Now this is not a very comfortable equation to work with because it is too singular an object. So mathematicians like to write this in the following form, and I will define this term. So this is written as dx equal to square root of 2d times dw t. This is called a Wiener process. The w of t is called a Wiener process, and let us write that down. I should put a t inside the bracket really, as physicists would, but mathematicians like to put it as a subscript because more notationally easier to handle there. Okay. And the practice, standard practice is to set 2d equal to 1. So you rescale matters in such a way that 2d is equal to 1, and then it is called standard Brownian motion. So standard Brownian motion or equivalently a Wiener process it is a Gaussian Markov process that is delta correlated. That is correlated in a specific manner, which I will derive in a second. Okay. This Gaussian Markov process eminently has most notable property is that it is not stationary. Non-stationary, it is a continuous process, that is important. Okay, with the following property. Okay. Essentially it is this x, and x we recall is the position, instantaneous position of a particle diffusing on the x axis with the diffusion constant d, and the probability density function of this x obeys the standard diffusion equation. Delta p over delta t is d times delta 2 p over delta x2, but for this process here we have set 2d equal to 1. It is clear that for this w, so the PDF of x satisfies of w, say, satisfies delta over delta t, let me just call it rho, equal to 1/2 delta to rho over delta x2. Okay. Pardon me? W of t is not white noise, it is the integral of white noise, because in a crude sense, quote unquote, dWt equal to zeta of t dt. So W of t, that is what I did here when I wrote this as dWt. We have to be careful about what I mean by this differential, and that is the whole point, right. So in this heuristic way of looking at it, this W of t is like the integral of white noise, because that is what zeta of t is. But the problem is that zeta of t is not a well defined mathematical object. It has got a singular covariance, it has got a singular correlation function, a delta function, which is not pleasant. Okay. Now think of what so W of t is essentially x, the position of a diffusing particle. Okay, that is it, apart from this constant here. But we know already what this guy does. We know that it is not a stationary process, and if the particle starts from 0, the origin at t equal to 0, then the position is a Gaussian distributed by a Gaussian with the variance increasing linearly with time, etc. And we also know that this process has an autocorrelation function which eminently is not stationary, which tells you, so Wt prime, the average, is equal to, do you recall what it is? Yeah, the minimum, the lesser of the two. Now we have set this 2d equal to 1, so with that normalization it is minimum of t prime. We are only considering positive values of t and t prime, right. So it is clearly not stationary, because the autocorrelation function has this behavior here. So let me stick to standard notation, write this. And this chap here has got the standard Gaussian solution, if you recall. This is implies fundamental solution rho equal to 1 over square root of 2 pi t e to the minus x square over 2t. I have set again at 2d equal to 1. Okay. So this is where it came from. Now let us try to understand this a little better. What this thing is, this is the covariance of t and t prime, that is the word for autocorrelation function in statistics. If you divide it by the covariance of this, and the standard deviation of this and that, so as to normalize it. So if you write it as sigma x sigma t, so how should I write this, sigma wt prime wt prime here over sigma wt prime, where this is the standard deviation of wt and that is of wt prime, and should be sigma squared here. By definition it is equal to this quantity. Then this is of course equal to min t prime over, and we know what this is, the square of this is 2dt and 2d has been set equal to 1, right. So this is equal to t square root of square root of t prime. This is 2d t and this is t prime, and we are taking the standard deviation, so root of t prime, and it is easy to see that this is equal to min t prime over max t prime, the whole thing square root. That is a convenient way of writing, easy way of remembering this. Now what can we say about the paths of this Wt? Okay. It is clear formally that the Brownian particle has got, Brownian motion has infinite velocity, because x squared scales like t, not x, and therefore delta x over delta t is formally infinite. You need to put another delta x on top in order to bring it to a finite value, right. Okay. So what do these paths look like? That is worth looking at, and a number of results are known in one dimension. Brownian path or sample paths of Brownian motion. We are talking about Brownian motion starting at the origin. So here is x and here is t and wt, the Wiener process starting here, and this process takes off and does this kind of crazy thing, it goes up and down, etc. And the following can be established rigorously from the properties of the Wiener process. The average is 0, we already know that. So over all such sample paths, you take the average, it remains 0 here. Okay. But the question is it differentiable or not? Is this differentiable? And the answer is no. I will just quote a number of results here. So nowhere differentiable, almost surely. So non-differentiable. Except on sets of measure 0, non-differentiable, almost surely. How badly is it non-differentiable? And there is an answer to that. It is a continuous process, and that is very, very important to remember. In fact, had we dropped this and had we required it to be stationary, what would the process be? Pardon me? Ornstein-Uhlenbeck, that is the only continuous Gaussian stationary Markov process, and it follows that it has an exponential correlation, and vice versa, the converse is also true in that case. But the moment you make it non-stationary but require it to be continuous, then you end up with Brownian motion. Okay. It is non-differentiable but it is continuous, therefore there must be some kind of Hölder continuity for this process. It turns out that the continuity looks like this: W of t plus epsilon minus W t modulus is less than or equal to some constant times epsilon mod epsilon to the power beta, where beta is less than half but can be arbitrarily close to half and not half except on sets of measure 0. arbitrarily close to half from below. Okay. So that sort of tells you how jagged these paths are. It is a measure of how jagged it is, because you can see that this will imply the function is not differentiable, because for differentiability, yeah, if you divide by epsilon, so it is clear that W t plus epsilon minus W t divided by mod epsilon tends, as epsilon tends to 0, it tends to infinity because of this property. It's going like half, so you divide here, you are going to get a half, little more than half in the denominator, and it is going to go to infinity as epsilon goes to 0. So it is therefore not differentiable. But this weirdness that it is Holder continuous with an exponent which is arbitrarily close to half from below means that this increments in this process are acting somewhat like square root of time. This epsilon is like the increment in time, right. So it is acting like the square root of dt, the infinitesimal dt. One can formalize that, and then you have to be a little careful, but by a clever amendment of the rules of calculus, one can actually handle this process quite rigorously. Here is what happens. Or to continue on the another property of the sample path, you can ask when does it cross 0, in a given time interval, how long does it stay above the axis and how long below on the average, and so on. In fact, you can ask where is this particle going to be most of the time, and it turns out there is a law of the iterated logarithm. This is Khinchin's law. So you plot for Brownian motion starting at t equal to 0, you plot the following function. This function is square root of 2t log 1 over t for small t, sufficiently small t, plot this, okay. And you plot the negative of this function here. This is minus the square root of this stuff. And if this is 1 plus epsilon times that function, and that is 1 minus epsilon times that function, so there is a 1 times square root, and this fellow is 1 plus epsilon times the square root here, and similarly here. Okay. Then the statement is almost surely the particle is either here or here in this range for arbitrarily small epsilon. Okay. So you not only have a statement about the probability density function of this x as a function of t or w as a function of t, but you also have a statement about where it actually is, what this part does, and yet the particle crosses the axis an infinite number of times. It does so in any arbitrarily small interval, and you can in fact ask what is the measure of the 0 set, the set of points where it crosses the axis. So 0 set, this would correspond to the set where Wt equal to 0. That 0 set in the limit has a fractal dimension which is a half. So while it can go arbitrarily far away, the 0 set is such that, by the way, this thing, the fluctuations obviously they are going to go way up there, way down here, and that is why the variance itself will increase with t, because the fluctuations are such that it is diffusing, although the mean remains 0 always. You can ask further interesting questions. You can ask what's the given some t here, what's the fraction of time for some capital T starting at 0, what's the fraction of time that it spends above the real axis, above on the positive side, and what's the fraction it spends on the negative side. That is a random variable.
Equal, right?
It's yes, but it's a random variable. Huh?
Oh, yeah.
One can ask what's the probability distribution of that random variable. So let us suppose, no, I am being incoherent. You could ask what if t is very large? You have a law of the iterated logarithm for t large as well. All you have to do is to replace that log 1 over t by t. Okay. But the crucial point is not that. The crucial point is this process is reinventing itself at every instant of time. It is what is called a martingale. I am not going to talk much about that, but we will see some consequences of what it does. It means that if you are here at this point, say you are here at that some instant of time, then the Brownian motion is as if it starts from there at this instant of time, and it again behaves in precisely the same fashion as it behaved earlier here. So at every point there is a law of the iterated logarithm at every time. The process has, the memory is very short, it is a Markov process. Okay. Now one can ask the probability distribution function. So let t plus be the amount of time such that Wt is greater than 0 for 0 less than t less than capital T. Okay. So we look at the Brownian motion up to some capital T and ask what is the total time spent where it is on the positive side and what is the total time spent where it is on the negative side of the x axis. The PDF of t plus, and similarly as you say t minus, it is completely symmetric. PD of t plus is proportional to 1 over square root of t minus t plus. Okay. Which implies that the cumulative distribution function CDF of t plus,
This looks like the oscillator.
it looks very much like the oscillator. Yeah, the time, instead of, if you have a regular oscillator and you ask dt, t is distributed uniformly over a period, you ask what is the distribution of the angle, it is precisely this 1 over square root here, many such distributions. Okay. Now the cumulative distribution function, namely the probability that t plus is less than equal to some given value tf, this thing here of course now is equal to, if you normalize it and you integrate this fellow from to 0 to t plus, you get 2 over pi sine inverse t plus over t. It should of course be 0 when t plus is 0 and it should be plus 1 when t plus equal to capital E. Total probability must be equal to 1, right. This is called the Levy-Arcsine law. Okay, now let us see what the fact that these sample parts are irregular, very jagged, they have very specific kind of irregularity, essentially characterized by the fact that the Hölder continuity is half, essentially half. That says that the following property can be rigorously proved, and this is part of what is called Ito calculus. And I will mention only the rudiments of it, essentially one formula, and it is the following. What one can prove is that for Brownian motion or a Wiener process, if you have on the time axis any 4 points, so let us start with T1, some point T2 and then some maybe T3 and some T4, and you ask what is this quantity W of W T2 minus W T1, so this minus that, and you multiply it by W T4 minus W T3, this thing here, the value of this product here is equal to the overlap between the two intervals. So, you have one interval from T1 to T2, another interval from T3 to T4, and the overlap between these two is this guy here. So, this is equal to overlap, length of the overlap between T2, T1 and T4, T3, T4. Okay. It has an immediate consequence. This, by the way, this statement can be proved by looking at the correlation, the autocorrelation, okay, and then it is a simple proof here. Now, this has immediate consequences. The first consequence is that dWt, dWt equal to dt, okay, because imagine a completely overlapped infinitesimal interval. Okay. The length of it is dt and that is the square of dWt. So, this is the one that formalizes the fact that this dW, the increment in the Wiener process is like the square root of the increment in time. Okay. This immediately has the following consequence. There are several ways of doing this, and what we are interested in is asking for the behavior of or the properties of functionals of Brownian motion. So, x is a random variable in the normal diffusion problem. Now, you ask what does f of x look like, where f of x is some function, etc. So, we are going to consider what happens if you had a functional, I just write it as FWT. You could extend it to the case where it has an explicit t dependence as well, we will do that in a second. What happens to this functional and what does its differential look like? Okay. What you have to do is to do a Taylor series about any particular point and keep track of the fact that this thing here is like dt. Okay. So, we will assume that f of whatever argument f of x is a continuous twice differentiable, at least twice differentiable. We will consider functions which are at least twice differentiable functions of the argument. Then we could ask what is df Wt. This is equal to f prime Wt dWt, that is the first term, right. But that is not enough because it is a function of a function. There could also be an explicit time dependence here. So, let me in fact write that time dependence. Let us look at the more general case where you have this then is well, let me use the following notation f prime, and I will explain this notation in a second. So, df of Wt t equal to this plus a portion coming from the fact that the second term in dWt will still be of order dt, and that term turns out to be 1/2 f double prime Wt t dWt okay,
plus the time dependent.
plus delta f of Wt t over delta t dt. Okay. But we know that this is dt, so it gets added to this term. Okay. This is the fundamental rule of Ito calculus. Where df over dWt is equal to f prime d2f over dWt. So, you differentiate with respect to Wt alone. Those are the two derivatives. We already assumed that, well, I should really write f of x comma t is twice differentiable in x. Okay. Now, the addition of this extra piece here helps you, that is the amendment that the rules of calculus need in order to be applicable to as singular objects as Brownian parts as a Wiener process. Because this is the differential form, the integral form of this will tell you what the correction is in normal cases. So, remember this rule, this here. Now, let us look at what is the integral of say T1 to T2, T equal to T1 to T equal to T2 of something like f prime of Wt. Let us look for the moment at functions which are not explicitly time dependent. So, you see what the correction is, dWt. What is this guy equal to? Well, we are integrating both sides of this equation here, and we are asking what is this fellow equal to. So, it is this integral, by definition it is a differential, therefore, you can write this as clearly f Wt2 minus f Wt1, that is certainly true. But then there is a correction due to this piece here. So, it becomes minus half integral T1 to T2 dt f double prime of Wt dt. So, there is this extra piece okay, which you require. Right. So, let us see what this is doing for us, what it implies. Let us first look at a case where this f prime of Wt, let us say, is Wt itself. Then it tells you that integral T1 to T2 in time Wt dWt, I should write T equal to T1, T equal to this, is equal to, by this applying this theorem, applying this blindly, it is the integral of this fellow which is Wt squared over 2. So, it is half Wt2 squared minus half comes out minus Wt1 squared minus half, well, f double prime is 1 in this case. So, it is just T2 minus T1. but this is equal to T2, right. We already had that overlap rule, and so the square of Wt squared is T itself. So this is equal to half T2 minus T1 minus half minus T1 is equal to 0, is identically equal to 0. Okay, because of the way this Ito calculus works. Now what does that actually mean? I mean, this is an important result because it tells you, this thing tells you that there is a specific interpretation being given to this process here, this integral here. So it says that what we mean by that integral, so since we can write t equal to t1 to t equal to t2 dwt can be written in the following way. So I start with time t, time 0, time t, and I break this up into n parts. So there is time t n, and time t n plus 1 is equal to t, and this is 0, so this is t1, this is t2, etc. Break it up. Then this is equal to limit n tends to infinity, summation from I equal to 1 to n times w ti times dw, but this dw is w t I plus 1 minus w t sub I here. It is the forward difference. Oh sorry, I am sorry, yeah, I chose it to be 0, yeah, I started with 0 t, yeah. This is a general result, this follows a general result here, but you can start at any point in this process. I start from 0, and that is the meaning of this. So it is this quantity that has been written there, and this fellow is this difference here in the limit as the number of intervals, number of subdivisions becomes infinity. Now this is the forward increment, and there is a current value of the variable. We know that the overlap between these two is 0, because this goes up to ti and this goes beyond that. There is no overlap between these two integrals and these two factors. Therefore, by our basic rule for Brownian parts, this is they are independent, this is 0. So that explains why you get 0 here. Okay. Now you could have interpreted it differently. When you do normal integration from a summation, you convert it to integration. There is no reason, so you normally write f of x dx, etc. Now you write it as a sum. This dx is say x plus delta x minus x, but this quantity here f of x is x at which point? It could be at x plus delta x over 2, it could be at any combination of f at x and f of x plus delta x.
So this is Ito's choice.
This is a specific choice of the way this integral is interpreted, the interpretation. So the fact that these two factors no overlap, and this guy here is the forward increment, it is this that gives you the Ito calculus and all the other properties that I wrote down. So clearly it says that there are other choices possible. You could choose this to be Ti plus 1, for example, yeah. Or you could choose it to be Ti plus 1 divided by 2. So you have any number of choices here, and each time you get a stochastic calculus. Okay. Now if you choose the Ito interpretation and you have this feature, then and only then does it turn out that the interpretation we have for the general Langevin equation or general Ito equation now. So our general Ito equation stochastic equation, I should not call it Langevin anymore. This is of the form some process dx is equal to some f of x dt plus g of x. Remember the Langevin equation that we wrote down with a drift term and a diffusion term. There was a g of x times, we called it white noise and put this as x dot, but the correct way of writing it is with the dt here, and this is dw in this fashion. This is an Ito equation. This is to be understood in the sense of Ito. So the x here, and if it was time dependent, the t is such that this is the x at instant t and this is the forward increment in the Wiener process. Okay. You need that interpretation, otherwise it is ambiguous. Multiplicative stochastic process is definitely ambiguous. So the question is, you have a noise in physical terms, you have a noise that is dependent on the state variable itself. The question is, state variable at what time? Okay. It is the state variable when you write the increment in x, it is the state variable at time t, where this dwt is the forward increment between t plus delta t and t. Okay. Then this implies and is implied by the Fokker-Planck equation that we wrote down for this process. It implies that the probability density of this thing is delta p over delta t is equal to, this fellow here is equal to minus delta over delta x f of x p plus half g squared of x d2p over dx2. Okay. So when you have a non-trivial noise, a multiplicative noise, you have to interpret it in the Ito sense, and then this is true. The Statanovich interpretation, where this would be Ti plus 1, would give you a different Fokker-Planck equation for the same stochastic differential equation interpreted in that sense. The point is that the physics has to be the same in both cases. So what would happen there is that you would have what is called a spurious drift term. So in going from the, you go from the engineering equation to two different stochastic differential equations so as to get the same master equation once again for the random variable, because that's, its moments are physically measurable. So you start with an equation between averages, the so called engineering equation, you add noise to it. If it happens to be stochastic multiplicative noise, you have to then specify, is the equation this equation in the Ito sense or in the Statanovich sense or anything in between. There are other interpretations, and then each time the prescription to go from the stochastic differential equation to the master equation changes in such a way that the final master equation is exactly the same for a given physical process. We have used all the way while I have used the Ito interpretation. It is sort of satisfying because of this, that it is not anticipatory, that it is a current dependence on the rate at the on the state variable at the current time and then the forward increment. Okay. But it is not sacred, it is not sacred. In fact, in physics very often one uses the Statanovich interpretation. Okay. But then you have what is called the spurious drift term. There is a correction to this fellow here, and the prescription to go from here to the stochastic to the Fokker-Planck equation changes in the two cases. We have consistently used the Ito equation. Okay. Now of course, if you use the calculus carefully, then questions of uniqueness come for solutions of this process. Questions of uniqueness arise, and here is an example due to Ito himself. By the way, I should give a reference to this whole business. It's the mathematical treatment can be made very rigorous, and one of the best places for it is the original book by Ito himself. So Ito and McKean, it is called Diffusion Processes. Recall that we called an equation like this a diffusion process, we called X a diffusion process. And you have to worry about the uniqueness of the solution to this sort of equation. We solved this for the Ornstein-Uhlenbeck case, it was completely trivial, this was a constant, that one was linear in X, and then it did not matter, we wrote down the solution. But if you do it rigorously, properly, then you have to be a little careful because you could have non-uniqueness. And here is an example due to Ito himself. So, we will work backwards to write the equation down. So, if you have example, this is due to Ito and Watanabe. And the equation is the following: X equal to Wt cubed, for example. You take this example, it is a nice functional of Brownian motion, right. Then what does the equation give you? It says dx equal to f of x, that is 3 Wt squared, so it is 3 times x to the power 2/3 dw dt plus the second derivative. You have to differentiate this is 3x squared, 3w squared, and that is equal to 6w divided by a 2, and w is x to the 1/3, and the 2 goes away in the calculus. So, get plus 3 times x to the 1/3 dwt. Sorry, that is the coefficient of how did I write this? It is the other way about. This is f prime, and then you had to do a dwt, right. So, it was this is dt, the correction part. So, if I ask what is the solution to this equation, we know this because we work backwards to get this equation. So, if I ask what process is this x, you would say it is Wt cubed from this guy, but you could also put 0 there and it gives you a solution. So, you have this or that. Therefore, the uniqueness of solutions is not guaranteed. Fortunately, this is a kind of academic example. Fortunately, it turns out that if you put in sufficient holder conditions on the continuity of this process, then you get unique solutions. Okay. For instance, if you can show that mod x at some time t minus x at time t prime is less than, sorry, the function. So, if this fellow is some function x of Wt, if you can show that x of in some alpha minus x of some beta modulus is less than some constant times modulus of alpha minus beta for all alpha and beta, all argument, then that suffices to show that the solution is unique here. This is not, this does not satisfy that. These two guys are not smooth enough at the origin, they are too singular at the origin. But if you have something milder like this, then the solution is unique, and that is what happens in most physical examples. Okay. Now you can ask, can this whole thing be generalized? No? But before that, let me point out, I think I have run out of time, but I should point out what the Feynman-Kautz formula is at the very least. Okay. This requires a bit of a preamble. Let me again motivate this on physical grounds. So, let me give a little preamble to this. Recall that the original diffusion equation, so let us write it in the physics notation. Our original diffusion equation was of the form delta P over delta T for the position of a Brownian particle d d2p over dx2, and you can ask what is the solution to this equation for some given initial distribution, not necessarily a delta function. Then of course you take the original Gaussian solution, use that as a kernel for the green function for the differential operator, and you integrate over the initial distribution, whatever it is. So you write the solution p of xt equal to 1 over square root of 4 pi dt, an integral dx prime over all x prime infinity e to the minus x prime whole squared over 4 dt. You could have started at any point t minus t naught, the initial time, you would have replaced this by t minus t naught. So we are talking about processes starting from the specified at x equal to 0. This multiplied by p, whatever be the initial, p initial of x prime. This was p of x at 0. Okay. It acts as a green function here. Now the Schrodinger equation for a free particle has exactly the same behavior, right. So there you have delta psi of xt over delta t equal to IH cross times that is minus h cross squared. So like write that as minus IH cross whole squared. So this is equal to IH cross by 2n d2 psi over dx2. This too has a similar solution, except there is this I. So it is as if the d were an imaginary quantity, and then it is not clear if this is an oscillatory function in that case. It is not clear if this thing converges. But formally, if you do a Wick rotation here in time and go to imaginary time I times t, then the two problems are mathematically equivalent and well defined. So you have exactly the same sort of solution. This would imply that psi of x comma t is equal to 1 over square root of 4 pi, and then instead of d you would replace it by IH cross over 2m t integral dx prime e to the minus x prime whole squared divided by whatever it is 4 times d is this, so twice 2 IH cross t and then an m or something like that times psi initial of x prime. And if you recall, this is the starting point of the path integral formulation of quantum mechanics. Then you do time slicing and stuff like that, and you get the path integral formulation of quantum mechanics, right. Now Mark Katz noticed this and said, now this operates in two different, gave a clever formula which essentially says that you can use this fact, the fundamental Gaussian solution, in order to write down solutions to some deterministic equations, or conversely starting with the deterministic differential equation, which is essentially the diffusion equation with a potential term on it. You can find expectation values of certain functionals of Brownian motion. It works in both directions, and in its simplest form it looks like this. So this is the so called Feynman-Katz formula. And let me write it in the simplest form. It has got all kinds of generalizations, higher dimensions, etc. But here is what it looks like. Suppose you have a partial differential equation, a parabolic partial differential equation in one space dimension and one time dimension, equal to, let us write the standard diffusion equation down. Okay. This is the PDF of a Wiener process, if you like, but along with that, let us suppose there is an extra term V of x times u of x comma t. If this were the heat conduction equation, it is like there is some external cooling which is state dependent, x dependent here. Or in the context of the Schrodinger equation, it is like a potential somewhere. Then the question is, what is the solution? You have to specify an initial condition, and the initial condition is, so some conditions are put on this. This is a non-negative continuous function. And u of x0 is equal to some specified initial function. So, this is u naught of x, and we will assume this to be continuous, bounded. So, it is a continuous bounded function. Then the statement is that the solution of this, the unique solution of this, has the following form. It is equal to the average value of e to the power minus integral 0 to t v of x, v of wt dt times u naught of wt where I have to say what is wt and what this average is over, where wt equal to standard Wiener process or Brownian motion, standard Brownian motion started at x at t equal to 0. So, you have Brownian motion started from wherever you want the solution, whichever point you want it at, and then you let it go and equal to average over all walks, all random walks. All sample paths. Subject to the above conditions, namely all Brownian motions starting at x at t equal to 0 at any starting at x, it is going forward right in time, and then you do this integral. Okay. So, this works both ways. If you want this where you have an arbitrary functional out here and here, some given functional, then you have this back again. Well, the simplest case would be v equal to 0, then you see where this is coming from. You put v equal to 0, this goes away, you are going to take the initial point and you are going to put the Gaussian kernel and you are going to integrate. That would be one way of computing the average, and that is exactly the solution we wrote down to the diffusion equation. But this generalizes it to the case of arbitrary functions here, subject to very mild conditions. Okay.
And this is just the path, I mean if you Wick rotate back.
If you Wick rotate back, it is just the path integral, Feynman path integral
for a potential.
For the potential v of x, exactly. But what is interesting is this is capable of enormous generalization. First of all, to higher dimensional Brownian motion, for which we know how to write, you have a general equation of the form dx equal to f of x dt plus g of x dwt, where this is an n dimensional vector, so is this, this is a new dimensional noise, and this is an n times d matrix with suitable conditions on the g's. We know how to write the Fokker-Planck equation down. Now for the process X, a general diffusion process X, you have an analog of this formula. It does not have to be standard Brownian motion alone. That would correspond to the case where f is 0 and g is 1. But you can, instead of Wt, you can use X and you can write a generalized formula once again for a more complicated equation here, which involves the first derivative of this u with respect to x with that drift term and the second derivative with that diffusion term here. Okay. So, instead of this operator, you replace it with g squared times this guy plus f times f of x times the first derivative du over delta x, and it is still true. So, higher dimensions, more complicated parabolic equations, it still works, this formula, and people have been at it for a very long time. I should finally mention that the case where this fellow is linear in x and that too is linear in x is the famous Black-Scholes model that is used in financial mathematics, and it corresponds to exponential Brownian motion. So, the random variable is e to the Wt, if you like, times some constants, okay, and then an explicit function of t to take care of Ito calculus once again. Okay. So, that is what I wanted to say here in this context. We have this entire course we have sort of started with very simple Langevin dynamics and come back to it in a very general form here. On the way we went through all kinds of applications of Langevin dynamics. That is a paradigm, that is a model, and I try to point out very briefly that the same model is generalized to the case of fields, order parameter fields, and then it has connections to both equilibrium and non-equilibrium phase transitions, how with the help of the Landau functional you got a handle on non-equal critical exponents, including dynamic critical exponents. We did not take an excursion into critical phenomena per se, that is a separate topic by itself, but we did study some linear response theory on the way, both classical and quantum, and some topics we have run out of time, and most notably chemical kinetics and the thermodynamics of very small systems, all the fluctuation theorems. These are two notable exceptions, perhaps at some future date. Okay, stop here.